All right, so what we'll do then, we've got about 15 minutes or so. Let's begin the process of starting to look at chapter 5 and just get a little bit of a jump on the material before tomorrow. So chapter 5 is all about nuclear chemistry. And so what we're going to see, the next 2 chapters, we are taking this idea of the atom and we are basically splitting it into its parts. On one side, we have the nucleus, and we're going to focus on the nucleus this week and the reactions that occur within the nucleus when the nucleus is not stable. And next week, we'll focus on the electrons and how the electrons interact with each other to create compounds to drive chemical reactions. And once we do that, we're actually going to take a brief break from this kind of overall chemistry series of concepts to start getting into some of the more specific parts of this class. We're going to take our first break into organic chemistry the following week, using those principles of molecular compounds to describe a very specific class of molecular compounds known as hydrocarbons. So hopefully what we see here, section 1 here is all about natural radioactivity, the kind of radioactivity that we encounter on a daily basis, on a regular basis, that we are encountering actually right now as we speak. And to understand radioactivity just in general, we have to be familiar with this kind of notation where we're looking at mass number here and atomic number, that symbology that we were working on at the end of last week. So again, we need to understand mass number and atomic number are describing the nucleus, and in particular, how many particles are in that nucleus. Atomic number tells us the number of protons in the nucleus. The mass number tells us the total number of things in that nucleus, including the neutrons. If I subtract the 2 from each other, that would tell me the number of neutrons in that nucleus. The other thing that we should have picked up on last week is that even though we have the same element in a lot of cases where we've got the same number of protons, it is possible to have 2 different atoms that are of the same element that are different from each other in that they have different numbers of neutrons. And we call those isotopes. So if I have an isotope of hydrogen that has no neutrons, and an isotope of hydrogen that has 2 neutrons, I've got hydrogen in both cases. Chemically speaking, they're going to react the same way. But nuclearly speaking, that hydrogen with the extra neutrons is going to have a much different experience than the one with no neutrons. That's where the isotope difference comes in. So just a little bit of kind of background information here. As we saw last week, most elements have more than one isotope. And if we get above element number 20, we start to see more and more elements that have unstable isotopes. And if we get above element number 83, we only have unstable isotopes. So element number 83 is bismuth. Bismuth is the last element that has stable isotopes. After bismuth, every single element, every single isotope of those elements are radioactive, meaning that they are unstable in some kind of way, and when they react, they are going to react in some kind of way to increase their nuclear stability. Now, how do they do that? They do that through radiation. Radioactive particles, that is those nuclei that are unstable, will emit radiation to become more stable. And in that radiation, we will see 2 things primarily. we will see the ejection of some kind of a radioactive particle, and we will see the release of a good bit of energy. And the relationship between the size of the particle and the amount of energy released is an inverse one. The bigger the particle is, the lower energy it's going to have. The smaller the particle is, the higher energy it's going to have, the more dangerous it's going to be. Now, radiation tends to come in 4 different kinds of packets. And which packet we get largely depends upon what isotope is undergoing radioactive decay and what kind of instability are we looking at inside of its nucleus. So we have what are called alpha particles. Alpha particles are in general heavy and the lowest form of energy. We have on the other side gamma rays, which have no mass. And so they are therefore pure energy, very high energy as a result. And then in the middle, we have beta particles and positrons, which are considerably light. Their mass is about that of an electron. And they have kind of a moderate energy as a result.
The alpha and beta particles are both heavy?
No. The beta and the positron are basically the same. So what's interesting about beta particles and positrons are what we call antimatter particles of each other. They're basically the same particle, only one has a positive charge and one has a negative charge. So imagine just for a second, let's say that we had an electron. Well, a high energy electron is kind of similar to a beta particle. Well, if I took that electron and switched its sign to positive, we would have what is called a positron. Mass would be basically the same, just a positive charge instead of a negative charge. And so if you've ever heard the term antimatter or antimatter, that's what they're referring to. They're referring to 2 particles that are pretty much the same in every way, but they have opposite charges. And when those 2 particles collide, that's when the real fun happens. Basically, their masses cancel each other out, and all of that mass gets converted into energy. The end result, a whole bunch of gamma rays. Yes. Yes, and we're getting there. Yeah, just give me a minute. All right. So just a little bit more terminology here. If I have an isotope that is unstable, radioactive, another term for that is a radioisotope. Basically, we're just taking radioactive and isotope and smashing the 2 words together. Now, when that radiation takes place, when that decay happens, the radioisotope is going to go through some kind of a fundamental change. That fundamental change is going to involve one of these 2 things. we are either going to see a change in the number of protons, a change in the number of neutrons, or both. Now, if we see a change in the number of protons, we know automatically that this is going to happen. Because the protons are the identity of the element. If I change the number of protons, I'm going to change the element that's there as well. And so what we see a lot of times here is we see this kind of composite idea that radioactivity is going to cause not only a change in the stability of the isotope, but it's going to cause a change in the identity of the isotope as well. So here are some examples of some stable and some unstable isotopes. So here's an example of a stable isotope, magnesium 24. Now, we talked about this just a little bit last week. When it comes to identifying an atom or an isotope, we can use this notation that we used a lot last week. We can also use this notation here at the bottom as well, where we just identify the element and its mass number. And so another variant of this would be like Mg24, where this number here refers to the mass number of the isotope. So there are actually three ways of identifying an isotope. Using the symbolic one that we saw last week, where the mass number's on top, the atomic number's on bottom, we've got the symbol kind of offset in the middle. But we can also use this kind of elemental notation with the mass number as well. Good question.
How are they radioactive? How are they different? Stable one on top.
Okay, so the question here, how do I know that magnesium 24 is stable, whereas these other two aren't? What's the difference? Well, it really comes down to unfortunately, I don't think the text gets too deep into this, but there is a relationship between the number of protons and the number of neutrons in a nucleus. So when a nucleus is brought together, there are, we kind of have to weigh against a couple of things. The protons themselves are going to repel each other because they're all positively charged. And so what comes a matter of is kind of a delicate balance between the overall size of the nucleus and putting enough neutrons in there to balance out the repulsion forces of those protons. And what ends up getting created, and it's not covered here, we're just gonna fake this here. All right, imagine, if you will, here a graph. And on this side of the graph, we've got the number of neutrons. And on this side, we've got the number of protons. if I were to graph every single isotope known to humankind on this graph, what I would find is that there is a balance between the unstable nuclei and the ones that are actually stable. It has a lot to do with that balance inside of the nucleus, meaning I've got a certain number of protons being counterbalanced by a certain number of neutrons. As our atoms get heavier, that balance shifts to being kind of co-equal partners to actually needing more neutrons in the nucleus to help balance all of that out. So if you look at the masses on the periodic table, the numbers that we told you not to look at last week, those give us an idea of kind of what the most stable version of that element is, if we round it up or down. So if you look at the first 20 elements, what you'll find is that it's really close to 1 to 1. 1 proton for every neutron, give or take 1 either side. So you look at carbon, carbon has 6 protons, its most common isotope is 12, which means it's got 6 neutrons. You look at calcium, calcium's atomic number is 20, its most common isotope is 40, 20 of each. But if you start going down the periodic table, you'll see that that balance of 1 to 1 doesn't work anymore. It starts to shift toward heavier. The reason it starts to shift toward heavier is you've got more repulsion to worry about with those protons. And so how do I know that this is stable and these ones are not? It's the ratio. It's the ratio. I know that with magnesium, 1 to 1, 12 against 12 is probably the most common form. 12 to 11 seems like it's really close, but it's just a little bit different. And in an atom that small, that little bit of difference is the difference between being stable and being radioactive. And in 27, now we're seeing a big tip toward neutrons. It's too big. So it's going to balance out. Radioactivity is going to take place to push it towards something that's more stable. So that's how we know. And I can share some resources to kind of explain that a little bit more clear. We're getting at a concept called the band of stability, which isn't in your book. I think it's kind of essential to understand why some are and some aren't. But in that band of stability, you'll see the isotopes that are stable, they'll start off very, very linear, 1 to 1, same number of protons and neutrons, but they'll start to bend up toward neutrons right around element number 20. And if you're not in that belt of stability, you're above it or below it, you'll find radioactivity. And where you are above it or below it actually dictates what kind of radioactivity you would see. Certain positions will yield positrons, certain positions will yield beta decays. Basically, alpha decays, alpha particles come about when you've got elements that are bigger than this. So that's going to get us started. If you're able to read that first section tonight, section 5.1, it's going to give you a little bit more information about each of these types of decays. We'll kind of come back on that on Tuesday, so tomorrow. Have a good day.